thank you so much to the organizers for inviting me to speak here, and also thanks to the IHES for hosting everyone and for offering this wonderful environment. So in this series of lectures, I want to explain a theorem and a lot of the background for this theorem. So in fact, let me state the result first, and then I will explain some of the things that I want to tell you about that surround this result. So this is joint work with David Fisher and Ben Lowe. And the theorem is the following. So we have M, a real-analytic Riemannian manifold. So for simplicity, I'm going to assume that it's closed, meaning compact with no boundary, with strictly negative sectional curvature. And so remember, sectional curvature is the thing that depends on a two-plane. So it's the more complicated of all the curvatures. And so there's several equivalent formulations. So one of them is that if M has infinitely many totally geodesic submanifolds, then M has constant sectional curvature. E, M is isometric to hyperbolic n space divided by a lattice. And there's an equivalent. So in this form, this is somehow a theorem about some discrete set of submanifolds. In other words, so a few remarks. So n. So I was a little bit sloppy. So a few important hypotheses. So first of all, I shouldn't have said submanifolds, but hypersurfaces. So I'll mention in a moment the case of a higher codimension. So here it's hypersurfaces, and n should be at least 3. So of course, sorry, this is a hypothesis, not a conclusion. So if you have a three-dimensional manifold or higher, and it has infinitely many totally geodesic hypersurfaces, then in fact it has to be one of these space forms, so locally isometric to a homogeneous space. So in this formulation, as I said, it's something about, it says that there's only finitely many examples, but there's only discretely many examples given by these lattices and acting on hyperbolic space. But there's a way to formulate it that tells you something about every manifold like this. So equivalently, M has only finitely many totally geodesic hypersurfaces unless it is a lattice, a quotient of hyperbolic space by this lattice. And so in this case, in this form, it's mostly a statement about finiteness. So it says that a general, an arbitrary. So one thing I want to emphasize about this theorem is that, of course, it has no genericity assumption. So I'm not saying almost every word that I can perturb it a little bit. I'm saying that literally every such Riemannian manifold has only finitely many totally geodesic hypersurfaces, with one exception. And
so you're not assuming any compactness assumption on the hypersurfaces?
So I was not going to discuss this point here, but for this statement, for the most general statement, I will assume that they're compact and immersed. There is a version where we don't need to assume compact, but then I have to make some further assumptions, which I will discuss maybe once I get to the actual theorem. So let me here add, just to be precise, closed and immersed. But there's ways to drop some of these assumptions. So I'll discuss the slightly more general version once we have enough background to talk about this. I should maybe also should have clarified what does it mean to be totally geodesic. So let me just say it in words. If you have a submanifold of a Riemannian manifold, it has an induced Riemannian metric and an induced notion of geodesics. And being totally geodesic means that the two notions of geodesics agree. So the extrinsic notion from the ambient manifold is the same as, so in other words, a curve in the submanifold is geodesic if and only if it's geodesic in the ambient manifold. One kind of complement to this theorem, and in fact, in some sense, the original one of the motivations for this theorem was that, so it's a result of Bader, Fisher, Miller, and Stover for all n. So this is for all n, and Margulis and Mohammadi for n equals 3. So their theorem is assuming that you're already in the homogeneous case. So if, let's say, a compact quotient like this has infinitely many totally geodesic hypersurfaces. And again, here I mean closed, closed and immersed. So then they have a conclusion about the group gamma. Gamma is an arithmetic lattice. So the key word here is arithmetic, meaning that it comes from a very restricted class of constructions of discrete subgroups of this group of isometries of hyperbolic n space. Just as a reminder, for a hyperbolic space, you only, so once you go to dimension 3 and higher, in fact, dimension 2 and it's also true, not all lattices come from this arithmetic construction. So there are lattices in hyperbolic n space which are not arithmetic for arbitrary n. So the only way you could have these infinitely many totally geodesic hypersurfaces is if you're arithmetic, and not just any arithmetic, but some specific class of arithmetic sublattices.
There is an arbitrary n greater than 3.
So let me, so I apologize. So Bader, Fisher, Miller, and Stover prove it for any n at least 3, and Margulis and Mohammadi prove it for n equals 3. Okay, any other questions? Let me make a few more general remarks. So the first one is that this is false in positive curvature. What I mean by that is that you can take, for example, the n sphere, and you can perturb the positive, the constant curvature metric to have it be no longer of constant curvature, but to preserve the existence of infinitely many totally geodesic hypersurfaces. So if you are on the n sphere, of course, the codimension 1 spheres, they have a continuous family of totally geodesic submanifolds, but you can perturb that metric real analytically, keeping it real analytic, and maintaining infinitely many totally geodesic hypersurfaces. And also, it's also false locally, and by that I mean that if you take a small ball in a negatively curved Riemannian manifold, real analytic, you can arrange it. I mean, you can construct real analytic metrics which have infinitely many totally geodesic hypersurfaces locally, but the question is how do they behave globally. Okay. So as I said, I'll get to the proof of this theorem, and the proof itself, you could probably present in just one lecture almost completely, but I want to spend a little bit of time trying to discuss a number of background topics. Some of them I think many people have seen, and I also apologize to the experts in the audience who I think will be maybe a little bit bored, so I think maybe I'll try to keep you awake by occasionally making some mistake, and you can try to correct it. But I also want to maybe revisit some topics which, at least for me, before we started working on this project, I didn't know about, even though, as you'll see, they're quite classical, and there's some very natural questions that one can look at. And I want to maybe set up the background so that one can start thinking about the slightly more general version of this theorem, where you can try to, first of all, ask if you can drop the condition of real analyticity. So as you'll see in the proof, this is a very useful condition, but you can ask if it's also necessary, and we don't know this. And the other condition that you might want to look at is you might want to drop the condition of hypersurfaces. So you'd like to have some theorem that covers also, for example, if you have totally geodesic 5 manifolds inside a 10-dimensional manifold, you would like to have some analogous statement. It will not be quite the conclusion that you are a homogeneous space, but once we have a little bit of background, I can try to state the general expectation that one would have. Yeah, and as you'll see, there's also a number of questions that one can formulate that are along in the spirit of this theorem about quite general Anosov flows. So the first thing I want to do is talk about just general hyperbolic dynamics, and okay. So
sorry, is the complementary statement, is it if and only if, or?
Not quite, in the sense that you can have some arithmetic lattices for which there are no totally geodesic codimension 1 submanifolds. So what is true in the arithmetic case is that if you have 1, then you have infinitely many. But you might have 0. So there's that slight subtlety. Any other questions?
It's true. It's shown that this arithmetic lattice is of simplest type.
Yeah, so one has to define.
Only if it is an arithmetic lattice of simplest type.
Yeah, so one has to go through the definition of arithmetic lattice, what kind of constructions there are. I mean, simplest type is simplest for the people who know how to define those things. And so one thing I want to emphasize is that in this course, I really want to talk about the general case, the non-homogeneous case. So many of these results are inspired by homogeneous dynamics, but we want to go to some kind of non-homogeneous setting. Okay. All right. So I want to talk first a little bit about hyperbolicity. And one thing that, at least when I first learned about this, is that people somehow talk about some examples, but if you want to develop a good theory, one of the best places to start is actually to look at linear maps of Banach spaces, not just so infinite dimensional spaces. And this turns out to be very useful once you're interested in studying not just a single linear map, but maybe some smooth diffeomorphism of a manifold, and working you can naturally construct some Banach spaces from that, and that turns out to be somehow a useful setting. So I'm going to consider the case where we have a Banach space, which, as a reminder, means that it is a vector space which is complete with respect to a norm, or a metric induced by a norm. And one thing that is important is that we want to not distinguish between equivalent norms. So two norms are equivalent. We will call them equivalent if there exists a constant greater than 0, such that for any E in E, we have the inequality that 1 over C, the norm of E in the first norm, is less than E in the second norm, and is less than C in the first norm again. So we're going to be interested in Banach spaces with a norm up to equivalence. So depending on convenience, we might switch to different norms. And we're going to be interested in linear maps A from E to E continuous. So maybe I should say, if you are worried about Banach spaces, you can just assume this is some Rn, some finite dimensional vector space. I hope to convince you later in this lecture that it's useful to consider just general Banach spaces. So I'm going to make the following definition, that we're going to say that A is hyperbolic if there exists an A invariant decomposition and constants C greater than 0, and then let me call this kappa S less than 1, less than kappa U, such that for any E in ES, we have that norm of A to the n E is less than or equal to C times kappa S to the n. And for any E in EU, we have that norm of A to the minus n E is less than C times kappa U to the power minus n. This is all for any n greater than or equal to 0.
You want to add the norm of E or C E?
Oh, yeah, I'm sorry, yeah. Norm of E, norm of E, yeah. Thank you. Yeah, so the condition is that up to some constant C, if you iterate the dynamics into the future, this linear dynamics, you get contracted. And if you iterate into the past, you also get contracted. So the picture is like this. So you have ES and EU. Actually, let me, there's many conventions about horizontal and vertical. Let me, I think, to not get confused later, I'm going to keep the stable vertical and the unstable horizontal. And the first remark is that this definition is independent of the norm. So if I change A to an equivalent norm, then I just have to change the constant C. So the first remark is that this is independent of norm. So just change C, but usefully not the constants kappas, the kappa constants. the other remark is that we can change the norm to have to an equivalent one, to have that AE is less than kappa, let's say S prime times norm of E for any E. So let me call this norm 1 for any E and ES, and kappa S prime slightly bigger than kappa S, but still less than 1. So in fact, for any number slightly bigger than kappa S, but I can modify my norm to an equivalent one such that I have this inequality in one iteration, and the same thing in the unstable direction. So the analog of this inequality. Okay, so already, of course, this depends on the norm because we see contraction in one step, but the advantage is that well, we have to lose a little bit of the constant, but we do see everything in one step.
Sorry, I have a question. If my space is infinite dimensional and very different norms, are you saying I can change my very different norm to an equivalent norm for S?
Yes.
But still you see this ergodicity.
So I'm saying that if I have a linear map satisfying this property, then there exists an equivalent norm such that this property holds in one for n equals 1 already. So you see contraction. You see, if you have this inequality for n equals 1, you can iterate it. And I have this inequality where C has become 1. Okay, so the difference between this and this, so if you want, maybe if I put n here, maybe it's a little bit more clear. But the crucial point is once you have it for n equals 1, you have it for all. So this inequality I can iterate, whereas this one, if I know it for n equals 1, C could be enormous.
Okay. You said that this is independent of the norm, but what if the norms are not equivalent?
No, equivalence in the class of equivalence norm.
So it depends on the equivalence class of the norm?
Yeah, so I'm saying if you have this for one norm, there's an equivalent norm for which that condition holds.
Then I'm talking about the first bullet point, the independence on the norm.
So I'm saying if this property holds for one norm, then it holds for another norm, for any equivalent norm, but with a different constant.
But not for any arbitrary other norm.
Okay, yeah, so maybe I'll say it in words. So we'll always consider only equivalent norms. So a Banach space, so for us, a Banach space will mean the space with a topology, and the topology is always the same. And if the topology is always the same, then the norms will be equivalent. So we're never going to change them.
Considering invertible edit?
Very good question. So in fact, you don't need to. So this is kind of so you know this point. So you don't need actually A to B. So I assumed here that it's continuous and in particular. So you need, if you actually look at the axioms, you'll see that what you need is that you're bounded on the stable space, and you want A inverse to be bounded on the unstable space. So you want these bounds, but it could be that on the unstable space, you could expand. You could be unbounded on the unstable space, and actually everything works just fine in the infinite dimensions. Okay, so I should say, so this is an exercise. So it's in the notes, I think, or maybe if it's not in the notes, you should do it.
If you replace the A inverse in E to E prime, and A prime is in EU, and I mean, I'm a little bit confused how to deal with the non-invertible linear. So sorry, my question is bad. Sorry.
So maybe if you're confused by that, you can just ignore the invertibility question. Just assume A is invertible. so let me maybe give you an important proposition. So we're going to see this later as well. So, so the following are equivalent. So the first one is that A is hyperbolic. The second one, so for this statement, again, if you don't know what the spectrum is, then you can just ignore it. But the spectrum of A as an operator on Banach spaces is disjoint from the unit circle. So, and here it's kind of important to consider complex numbers. So concretely, this means that for any z and c with norm of z equals 1, A minus z is invertible. So in other words, yeah, so it has a bounded inverse on both sides. At two sides, it's important that it's a two-sided inverse. And the other more geometric criterion, so this is called the cone criterion, is that there exists an equivalent norm on E such that and a decomposition E equals E1 plus E2. So here's important, not necessarily A invariant. So the decomposition is not necessarily A invariant, such that if E equals E1 plus E2, so let me write it like this, such that if we set this cone C to be those E so let me draw the picture. So when the norm of E1 to be greater than or equal to, so let's say, yeah, greater or equal to the norm of E2. So this is the cone C. Then A of C is contained in the interior of C. And similarly, so we call this 1. Similarly for C2. So what this second version of the hyperbolistic criterion says is that you might not know precisely where your unstable direction is, but if you can find some guess for your stable and unstable directions, E1 and E2, and then you take cones around them, and if those cones are mapped into themselves, then actually it tells you that you are hyperbolic. So in other words, there will be such a decomposition which is actually A invariant. Okay? So and the way you construct such a decomposition is you take this cone and then you iterate it. So after another map, after one iteration, it will shrink like this, and then you keep applying it until you get a nested sequence of cones, and you construct the invariant subspace this way.
A of C1 is contained in the interior of C1.
C1.
Excuse me? I'm guessing you always assume the subspaces to be closed?
Yes. So whenever I write such a decomposition, I mean that the subspaces are closed And if I write the norms, I take a norm on each component, then it gives me an equivalent norm. Yeah, so this, I would say this is a kind of a continuous decomposition. Yeah. So you write the same condition for the 2 subspace. Yeah, an A inverse. Yeah, so you should, if you have, so I think some people have seen these kinds of things before and some people haven't. And if you haven't, then a good exercise is to fill in. So if I'll try to write the condition for the stable direction, and you should fill in the symmetric condition for the unstable direction. Okay. All right. Any questions? All right. So now let me discuss a little bit the notion of stable manifold or unstable manifolds. Or actually, let me do the unstable. So we suppose that A from E into itself is hyperbolic, and E is ES plus EU. So what we're interested in is a perturbation of A. So we're going to consider a map F, capital F, which is A plus little f, and F from E to E. I'm going to say that it is L Lipschitz with f of 0 equals 0. So you should think of the case when you have a general smooth map and you have the linear part, and then you have the higher order terms, which are the little f. And in particular, this Lipschitz constant, you can make it arbitrarily small by maybe shrinking some neighborhood. Okay. So maybe let me just give you an exercise first, which is that if if f of 0 is not equal to 0, and but norm of f of 0 is sufficiently small, and L is sufficiently small, then f has a fixed point near 0. So you know that if you have a contraction mapping, then if you perturb it a little bit, it's going to still be a contraction, and it's going to have a fixed point. So it turns out that this is also true more generally. If you have a hyperbolic fixed point, then if you perturb the map a little bit, then nearby there's still going to be a fixed point. So in particular, this assumption is kind of harmless, because if you move not too far, then you can just change your coordinates and get a fixed point there. Okay. So the unstable manifold theorem again refers to this f. Let me try to draw the picture first. Oops. See, yeah, there's colored chalk. Yeah. So we have the unstable direction for the linear map, the stable direction, and yeah, sorry, oops, yeah, this is, yep. So, by the way, one thing I learned at some point was that, so there's a convention, unwritten convention, about stable and unstable manifolds, so which colors to draw them with. And so you're supposed to draw the unstable manifolds with red and the stable manifolds with blue. And it's supposed to have to do with blood flow in the humans or in any animal. So red blood comes out of your heart with oxygen and it's red, and the veins, they're blue. Actually, veins are blue not because the deoxygenated blood is coming into the heart, but basically the convention has to do with veins which are in blue and the arteries which come out in red. So anyway, so unstable manifolds, whenever you draw an unstable foliation, it should be red, and the stable one will be blue. This way you'll never get confused if you draw these pictures, if you follow the convention. OK, so what is the statement is that there exists a continuous map. So assume L is sufficiently small, the Lipschitz constant. There exists a continuous map, let me call this phi u, from EU to ES, such that if I'm going to denote the graph of phi u, which is the set of points E phi u of E inside EU plus ES, the graph of phi u. So a few properties. So is F invariant? And so let me draw the picture. So if you actually try to do this on a computer, if you take a little cloud around your origin and you start iterating into the future, what you'll see is that your points will start to really accumulate along the unstable manifold, because your dynamics is kind of contracting vertically and expanding horizontally. So if you take this little cloud, it's kind of going to become like a pancake or a crepe in France. So it's very thin and spread along this red curve. So in symbols, it says that gamma of phi u is equal to the intersection. No, sorry. Gamma phi u intersected with so ER. So let me call this ER is the set of E in E such that the norm of E is less than or equal to R. This is equal to the intersection, as n is greater than or equal to 0, of f to the n of ER. Yeah. So if I concentrate in a small neighborhood and I start iterating it, then the points which will have infinitely many preimages in this neighborhood will be exactly the points on this unstable manifold. And as you would also expect, that if E belongs to this graph, then the norm of f to the n E is less than some constant times some kappa u prime to the n for some c greater than 0 and kappa u prime slightly less than kappa u, but still greater than 1. So if I iterate things backward, then I get exponentially contracted into the origin. There's a bunch of other properties which I'll comment on in a moment, but let me ask if there are any questions. OK. So let me so I will not prove this theorem. I will say that there's kind of a nice formalism, which some of it is in the exercises. But one thing that is nice about this hyperbolicity theory is that the right kind of regularity setting is the one that I wrote here, which is you have a linear map, and then you take a Lipschitz perturbation. And for example, you can prove a nice inverse function theorem, not for, so you know the inverse function theorem for C1 maps. It turns out that there's an inverse function theorem for Lipschitz maps, where you take a Lipschitz perturbation of an invertible linear map, and you have also a nice inverse function theorem in that setting. In general, it takes a little bit of work, but it is true that, so in general, phi u is as regular as our perturbation f. For example, ck if f is ck. So for example, if my perturbation is smooth, f is smooth, then my unstable manifold is also smooth. And if it has two derivatives, then this thing has two derivatives, and so forth. So this is a general principle. It takes a while to prove this kind of stronger regularity. If, for example, f is analytic, then the unstable manifold is analytic. OK. Any questions? Yeah? Oh, yes, yes. I always forget this. Yeah. Yeah. OK. So I wanted to maybe I'll do this once we get to that situation. But it turns out that for the existence of stable and unstable manifolds, you don't really need such a strong requirement that you have hyperbolicity. It's enough to have a decomposition which is invariant, and for which you have contraction, faster contraction in one direction than expansion in the other. So I'll give you the analogous statement once we need to use it. But now I want to move to something that is maybe a little bit kind of closer to the original theorem, which is that I'm going to go for a second to manifolds. Oops. So before we go to manifolds, though, I want to maybe consider the following situation. So I'm going to have a compact metric space. I'm going to have f from x to itself a continuous map, maybe even Lipschitz if you want. So I want to maybe clarify. So in general, we're going to be interested in the case when X is a manifold. But oftentimes, you'll find yourself with some closed invariant subset in a manifold. So M is the ambient manifold, and X is a closed invariant subset. And of course, that closed invariant subset there's no need for it to be a manifold itself. So that's why it's good to at least make definitions where you have a arbitrary compact metric space, things like a counter set or things like that. And so I'm going to say E over X is a vector bundle. So another point which I'll assume that you know how to fill in that definition is, of course, I could just take a trivial vector bundle, in other words, X cross Rn. But I could have some kind of maybe a little bit more objects which are a little bit more interesting, which locally on X look like X cross Rn. But there's some gluing maps that introduce a little bit of topology. But again, if you're not comfortable with vector bundles, you can just assume this is X cross Rn. So a cocycle on E is a map, and we call it Fe from E into E, which is fiber preserving and linear on fibers, and which covers F, little f. So in other words, I have my X, and I have here X, I have f of X, I have my fiber E of X, I have my fiber E of f of X, and I have a linear map between them, Fe, if you want Fe of X, between these fibers. Okay. So let me assume that this cocycle is continuous. This vector bundle at least has a continuous structure. So the gluing maps are at least continuous. So the definition is that Fe is hyperbolic if there exists if there exists a pointwise decomposition E of X into stables and unstables, and constants C, kappa of S, kappa of U. So kappa of S less. So these are separated in this manner, such that for any E, for any X, for any E in ES of X, the norm of Fe to the n of E is less than or equal to C times kappa S to the n times the norm of E. So you get this contraction, and the same thing for EU, but in negative time. Okay. So now instead of having something in a fixed vector space, we have a family of vector spaces that depend on the point. And there's an so if you remember when I defined hyperbolicity, I said that there's I gave you several equivalent formulations. It turns out that the same is true here. There's several different formulations. One good exercise is that so if E is a Holder vector bundle and F is Lipschitz, then ES and EU are automatically Holder. So in this definition, I didn't assume that this decomposition varies continuously on the base point. And turns out that it's not only continuous, but it actually varies Holder continuously if you change the base point. Okay. So again, this is in the exercise sheet. Maybe one fun proposition which you can try to prove is the following, that yes?
Are these constants like independent to X?
Yes, so the constants, yes. Okay. Yes, so the way I wrote it, I think, yes, it should be independent of X. So one fun proposition is that Fe is hyperbolic if and only if the linear map, let me call this Fe. So I have the space of continuous sections of this vector bundle. So Fe of a section sigma at x is, somebody call this, I'll just write it like this. For a section sigma, what I do is I push forward the section sigma. So in other words, if I have a section from x to e, then if I want to know what is the section at, say, f of x, I push it forward. So then I want this to be a hyperbolic linear map on this Banach space. So this turns out to be useful for questions like, so one theorem, I'll mention it in a moment. So now suppose M is a manifold and F from M into itself is a diffeomorphism. We're going to say that F is Anosov if df acting on Tm, the tangent space, is hyperbolic. Okay. So if the action on tangent vectors has this hyperbolicity property, meaning that you have a decomposition to stable directions and unstable directions, and stable directions get exponentially contracted, and unstable directions get exponentially expanded. Okay.
Are your cocycles continuous?
Yes. So I'm always assuming that E is at least continuous. Yeah. And the map, yes, the map is also continuous map. And in fact, I also, for that exercise, for example, I need to assume it's at least Holder, for example. OK. So one place where, for example, a statement like this can be useful is to actually prove the following theorem, which is that if you have an Anosov diffeomorphism, if you perturb it, it is conjugate to, topologically conjugate to the original map. So it's a theorem. I'm not sure who to attribute it. Maybe it's a bunch of people. Maybe, I don't know, alphabetically would be Anosov. I think the proof I have in mind is due to Mather, Smale, and many other people, which is that so Anosov diffeomorphisms are structurally stable. i.e. For a, let's say, C2 perturbation f prime of f, of an Anosov of f, there exists a conjugacy, homeomorphism, H from M into M, with the following properties. So if I'm going to write, so if this is my original map, and this is my new map, f prime, and then I have an H, which topologically conjugates the dynamics. Okay? And the way you would, one way to prove such a theorem is to use these kinds of implicit function theorems or inverse function theorems in Banach spaces to basically construct H as a small perturbation of the identity. Okay. All right. So let me end this lecture with maybe a concept which, at least for me, a year or two ago, this was kind of a new concept. So there's the notion of quasi-hyperbolicity. So the situation we're interested in is that we have some Anosov diffeomorphism, and inside of it we could have a submanifold which is invariant by the Anosov diffeomorphism. So the question is, what can we say about such a thing? So let me give you first the theorem. I think this is due mostly to mania, or at least the hard part is due to mania, which is the so suppose Fe from E into itself is a cocycle over a compact X. So then the following are equivalent. So the first one is that for any x, for any E and E of x, the set, the orbit, Fn to the E, the norm. So this is a continuous cocycle. This norm over all n and z is unbounded. So it's a deceptively weak condition. It says just that if you take any vector, if you iterate it either into the future or into the past, you get something arbitrarily large. You'd think that this should always happen. Like, how could it not? But it turns out that this is equivalent to there exists a hyperbolic cocycle E prime and an equivariant embedding of E into E prime. So the picture you should have in mind is that you can have your stable and unstable subspaces of E prime, and your cocycle E could sit in here diagonally in some way which is kind of invariant for the dynamics. But so maybe let me observe one thing, that if you have a vector inside the hyperbolic cocycle, it will grow either into the future or into the past. Typically, it will grow in both directions, but if it belongs to one of the stable or unstable subspaces, it will grow only in one direction. So the equivalence of the fact that 2 implies 1 is obvious. The non-trivial result of mania is that 1 implies 2. So in other words, you can create a continuous cocycle and embed your cocycle into your hyperbolic cocycle E prime. And there's also a spectral characterization, which I think is also kind of nice, which is that if you have Fe acting on the continuous sections, satisfies that this map 1, the identity minus Fe is injective and has closed image. So this is kind of a functional analytic characterization. So remember, hyperbolicity means that this is invertible, but it's a little bit stronger than that. Not just this is invertible, but for any complex number of absolute value 1, this still remains invertible. And here, for quasi-hyperbolicity, you have kind of analogous characterization. OK, so I think my time for today is out. So what I plan to do next time is maybe continue a little bit with this notion of quasi-hyperbolicity. And as we'll see, there's kind of a dual notion. And then we're going to talk about geodesic flows and hyperbolicity properties of geodesic flows. And then we're going to kind of start looking more closely at geodesic flows and kind of associated geometry.
Questions for Simion?
Maybe just a clarification on the statement of number 2. You're saying that there's another vector bundle over X and then a cocycle F sub E prime, such that this is an embedding?
Yeah.
So E prime is not a cocycle.
No, E prime is a cocycle. So I can enlarge my E to another cocycle, which will be hyperbolic.
Okay. We labeled F sub E as the cocycle.
As the map, yeah. So there's a map. Okay, so there's a map. There's an embedding like this, and here I have Fe, and here I have Fe prime, and I can yeah. So this thing commutes.
So the cocycle is Fe prime.
Sorry?
The cocycle is Fe prime, E prime itself.
Yeah, so, okay, so if you want E prime and Fe prime. Okay.
So maybe to follow up on this, in Manier's paper, he somehow, the way he actually phrases it, he also makes X bigger, and you're saying that he actually does this and not. This is a step in terms of what he's doing, or?
So, but if you make X bigger, you can restrict to X. So.
Oh, okay, yeah, sure. That makes sense.
Yeah. So I will say one thing maybe about this theorem, which is if you look at Manier's paper, it's a pretty. It seems like an elementary theorem that should be provable by general methods. He kind of has to mess around with a lot of concrete things. I mean, yeah, I think it would be interesting to have a kind of a simpler proof of this theorem, because at least Manier's proof of this is quite intricate, I would say. And it's not too bad, but it's not something that I can easily explain.
More questions?
In Manier's theorem, if E is holder, then E prime is also holder.
I don't think he can claim that. I mean, yeah. So there's some strengthening that he does have, which is that he can kind of make it so that kind of as a norm, he can control the norm of this embedding. So somehow the complementary subspace, you can control the dynamics on the complementary subspace, but not. I don't think at least the proof gives any holder regularity.
Any other questions?
Yeah, something to clarify in your unstable manifold theorem, that the second bullet point, do you mean R to be like any positive number or sufficiently small?
Because of the way, so let's say for sufficiently small. Although some of these things, because if I assume little f to be globally Lipschitz with a small Lipschitz constant, I think some of these things will be true globally. So.
Thanks, Simion, again.